Good evening, everyone. It's great being here again at WarsawJS, albeit virtually. As Piotr said, I've been to the last two ConfrontJS conferences, and I really like the community. Everyone that I've met is so warm and enthusiastic, and I actually feel at home in your community. I wish I could come this year as well, if the COVID would allow. So let's start with a short story. Anyone knows this scene? You can write down in the live comments or not. So when I've read the ECMAScript spec, I felt like Neo from The Matrix. Okay, in this scene, Morpheus, the guy in the picture, offers Neo a choice. He could remain with the rest of the world, living happily in some dream world, or he could take a red pill and leave the Matrix to face a not so convenient truth. And this is kind of how I felt when I've read the specs, because the specs, the ECMAScript spec talks about jobs, realms, context, lexical environment, and lots of blah blahs. And everywhere else, you hear about the event loop, promises, timers, Ajax, animations, and so on and so on. Everything that the JavaScript developer hears about all the time. So where do the stuff that we hear about all the time come from if the ECMAScript spec doesn't talk about it? So that's kind of the theme of my talk. I'll try to bridge this space, and hopefully you'll understand more how JavaScript works and how you can improve your applications through that knowledge. A bit about myself, those who don't know me. I'm a software architect at Vonage, just joined a week ago. If there's anyone in the crowd from Vonage, you can shout out now. I was a neuroscientist. Finished at 2014 when I started doing JavaScript. I'm also an egghead instructor. You can watch my videos there, mostly about performance, but also about web components. I've been developing since I was 8, so I've had some experience with several programming languages. You can see JavaScript because it's obvious that I know JavaScript. And I'm also a runner, and I'm on Strava, which is the Facebook for athletes, but I'm only running, so I'm there for the running part. I also have 3 running projects right now, which I love the most. My 3 lovely kids, and they take a lot of my time. As I said, I'm coming from Vonage, so one slide about Vonage, just so you know what I'm doing. Vonage is cloud-based communications platform. It allows you as developers to embed all sorts of communications in your app. So if any of you is interested to connect WhatsApp, Facebook, SMS, phone, to auth, and everything that's connected to communication in his apps, totally free, can go to the link at the head of this slide and try it out, try the API for free. I'd love to hear your feedback. I think it's amazing, especially at this time when we're trying to connect the world together. Okay. So what are we going to talk about today? We're going to talk about the call stack. You'll know what it is by the end of the talk if you don't know what it is now. We're going to talk about the event loop and all the queues that it manages, where the set timeout goes to, where it comes from, events and promises. We'll talk about performance implications of this knowledge, so you'll actually have something to do with that. We'll connect it to your code. And we'll talk about Node.js, how the event loop works in Node.js and not only in the browser. So we'll start with the call stack. Actually, surprisingly, when you look at the ECMAScript spec and you're looking for call stack, you actually find 0 results. There is no mention of the call stack in the ECMAScript spec. What Morpheus would tell you when he gets you to the real world is that it's not a call stack. It's called the execution context stack. Okay, different name, less friendly, I guess. I'd rather have shorter names, but that's how it is. And I'm going to explain the better part, the better way to do it, to say it. So what is the call stack? So the call stack is this thing. Okay, not really, but it's, let's say, place in memory or whatever that functions get into and being ran. So it's the current synchronous process that is running in your program. So we have the main, which enters the call stack. Main calls func1, so func1 enters the call stack. And func1 only logs, so it finishes and is removed from the call stack. And now main calls func2, which calls func3 inside the log. Func3 finishes, just returns 2. And func2 finishes, main finishes, and again, we have an empty call stack. So this is the call stack. Anyone knows the website Stack Overflow? Now I need someone to vote for real, because I'm going to ask a question. I need truthful answers. Anyone copy-pasted code from Stack Overflow into production? Nobody. I guess someone in the crowd did. So Stack Overflow is when the stack overflows. Okay, here's our stack, and we have infinite recursion, and eventually this main function call overflows the stack, and we get a message saying that. So how does it relate to your code? Let's look at this code. Okay, this retry function, what it does, it tries to log window.myvar.myvalue, and if it doesn't exist, it fails. It throws an error. The catch, what the catch does, it calls the function again. So if we'll have this, it will just log it and exit the function. Okay, and when would this window myvar, my value, will be in the window? It will be when the set timeout finishes after a second. Okay? This sets the myvar with my value equals to 5, and we'd expect to see this logs 5. But the problem with that is that it's going to cause us Stack Overflow. Okay, what happens is that the retry calls itself synchronously, and we have this infinite recursion that we saw in the illustration before. So, yep, exactly, Stack Overflow. You go to Stack Overflow to see how to solve Stack Overflow, but can anyone think of a solution to that? You can write it down. Okay, a bit slow, but I'll share with you the solution. That's a help. But first, we'll see why it happens. This is how the Stack Overflow looks in the wild. I just profiled this retry script, and I see that we have one synchronous process. Okay, you see this task over here? This is one synchronous process running and calling retry again and again and again. And actually, when I, okay, all this red part, when I search for retry, I get 804 calls to retry before the stack overflowed. Okay, and I got the answer. Interval or set timeout, and that's the correct answer. So let's retry again. And we look at this code. We change our retry, and we use set timeout this time instead of starting with a try. And what happens is that the try is being called asynchronously because we use set timeout. So let's see how it works actually in a real example. So I'll just open, hopefully it will open, yeah. So you see it logged 5. We didn't have the call stack thing. So it's the exact same code. And let's just look at the performance tab. Refresh, logs 5. And now we can look at what happened here. So let's look for retry in our recording. So we see we have 221 retries. This is the page reload. It's not very important. But this is the part where our function ran. So it ran for 221 times. And the interesting part is where server response was called. This is the last time. Okay, so let's focus on this server response. And here we see our timer that fired. So it called a function, and it called retry again because the try failed, and it called the retry inside the catch. And then our timer fired. So we see there is a time difference between when like a blank spot with nothing running. So this gave this timer an opportunity to actually fire the change to set up the myvar, and the next time timer fired, we see that it just logged. We don't have the retry again. And this is when our log happened. Okay, so we set timeout, and sometimes we do it. We just add it and things work, like we used to do like that $timeout in AngularJS at the time, and things magically happened. But where do the timeouts go? Okay, and leave our code to run. So you could look at the ECMAScript spec, and Morpheus would tell you something like this. If you'll read it, I hope you'll understand. Just remove the async context from the execution context stack and restore the execution context that is at the top of the execution context stack as the running execution context. Okay. If anyone understands this, you can leave now because you know everything I want to say. But if the rest of you are like me, who don't really understand what's written here, let's try to explain it in a different way. So we have your call stack here, and we have a code. This code listens to a click event. And this click event, when it's clicked, it has this callback, and this callback gets to the event loop. And here comes our new player, the event loop. The event loop is the gatekeeper for the call stack. If the call stack is empty, the next callback in the queue enters the call stack. So here's our click. It calls async call, which is this, which calls set timeout here, and then it finishes. Okay, and then it calls sync call, and then sync call finishes, and we're done. But let's say this sync call or async call took a lot of time, and our frustrated user clicked another time on the same button, for instance. So what happens is, because the call stack is full, later click awaits here, and in a place called the callback queue. But where did this click come from? And where did our set timeout go? So what happens right now is that click finished, later click enters here, the event loop would get later click inside. But let's see where he came from. It came from a new player in our story, the web APIs. The web APIs are something that is in the browser. It's not part of our JavaScript. And it handles a lot of stuff like events, timeouts, AJAX calls, read and write, and rendering, and all that stuff. And what happens in the code is that if we have something, let's say set timeout or network request, we ask the web APIs, could you take this callback that I send you from the set timeout and just put it back in the callback queue in 100 milliseconds or a second or whenever we tell it to do. So now we understand where set timeouts go and how we get the callbacks have this delay that we saw in the profiler. So let's take a deeper look into the callback queue itself, okay, because it's a bit more complex there. And we'll see how promises get into, and promises and animations get into play. So what Morpheus says is that host environments are not required to treat jobs uniformly with respect to scheduling. Future features may add jobs that are not treated at such a high priority, which is a lovely sentence. There's another sentence in the middle that I moved away, but it's probably not so understandable. It's quite vague. What he means is that in this callback queue that the event loop is managing, you can have many queues. And these queues can run in different priorities. And let's see how JavaScript uses this in order to make our apps run. So if you remember, we had a task running in the profiler when we saw this synchronous retry that caused the Stack Overflow. And these tasks are scripts that run inside the script tag or callbacks from timers, for instance, like we saw with the set timeout. So if we create an algorithm for our event loop, we have an infinite loop, while true, that has some tasks list. It pops the next task and execute it. And then it goes infinitely until we have no more tasks. And then we can add tasks from the outside, from the web APIs, and so forth and so forth. But if we look at the spec, it says that we don't limit it to one queue. So we have several queues, and we pick one of the queues, we pop from it something and execute it. So it's the same thing, only we have several queues, and we're good with that. Okay, so you can actually use, let's say, the timers and user input. Okay, but that's okay. It's very simple. The next thing we need in the browser is to repaint, because we want to show the changes to the user. So repainting happens every 16 milliseconds, but only if we trigger it. And what do you mean by trigger it? You can go to CSS triggers and see what triggers CSS, like style and layout calculations. And this will cause our rendering to actually work. So now our algorithm looks like, again, the infinite loop, the tasks list, and we ask, should we render according to the 16 milliseconds and the triggers? And if we should, we render. And this happens on every loop of our event loop. The third part in our event loop is the part you've been waiting for: promises, observers, like mutation observer, and an ability to add microtasks manually. So all of these are called microtasks, and they are special in this way. So we have our tasks list, but the microtasks is a different list, okay, a different queue, that on every iteration of the event loop, it runs until completion and then continues to check the rendering. So we have one task from the tasks list, and all of the microtasks probably created here are running to completion, and then we check if we should render. Okay, pretty simple. And we have one last part for our event loop, which is the animations queue. We all know request animation frame, and if you don't, you should. It runs on every render, and we add it here. Okay. We just use request animation frame and callback, and it enters this part, and this runs all of the callbacks that we stacked over here in the last frame. So this is how our event loop works. It puts things into the call stack, either from the timeout from the web APIs, in the task list, or in the microtasks for promises, observers, and manually queued microtasks. And it renders and runs animations every 16 milliseconds or when something changed. So how does this affect your code or your application? So again, Morpheus says a lot of things about performance. I'm not going to read this because it's scary, but you can read it in your own free time. But let's see something that you hear a lot. A lot of developers hear and say that set timeout is inaccurate, and they can't really pinpoint why. And it connects to the former great talk about we need to know why this happens or how this happens. So the timeouts enter the tasks queue, okay? And the tasks run one at a time inside the loop. So we have other tasks that might run before it. We have the microtasks that run during this loop, and we also have the rendering to cope with. So let's see what happens in this simple application. Open the log again. Okay. And for this, I only need the console. And this, I'm going to count the time. And what it does, it creates a set timeout that only runs this noop function. And we see that it took 100 milliseconds. But now I'm going to count the time it takes the set timeout to run if I call a long task right after it. Let's see how it happens. So I call set timeout. I call set timeout, and then I call the callback. Okay, so when the set timeout is set, the callback is still in the call stack. So the event loop doesn't let this set timeout callback to get into the call stack. So I do this, and I see that it takes a lot of time because this long task is taking a lot of time. We add 1 million objects into an array. It takes some time, and I don't do it so good here. Again, let's see it with rendering. What I do here is I add 7,000 divs into the DOM. So I count the time, and I see that we are, 62 seconds, not so bad. But if I start to add more and more and more, so the rendering takes much longer. So now I have almost 100,000 divs, and I see that the time it takes to render takes much longer. So my set timeout is stuck, totally stuck. So this is why set timeout is inaccurate, because too many things interfere with it. Another thing is iframes and child windows. Child windows and iframes run on the same event loop. Okay, so if you do something that is intensive in an iframe or a child window, you'll get performance issues. So for instance, one thing you can do with iframes is to use web workers. So let's see an example for that. That's like a really mad thing because I'm doing an iframe for myself, so I can see it indefinitely, but it doesn't matter. We have a button that just adds a counter. And we have this script that does something horrible. We just do a while loop for 5 seconds. So if I click it, so nothing happens. I just click on this button, and I can move aside. And you see, it just put these clicks into the callback queue and handled them when the call stack was empty. Okay, so you might say, hey, this is like a sandboxed iframe, right? But no, if I click on horrid here, I get the same effect. Okay, but if I use a worker to do this job, and you can see this worker script just runs this function, do something horrible. So I'll just click here, and I can keep on using my parent window, which is pretty cool. So just know that if you're using iframes, this can be an issue, performance-wise. Another thing is child windows, which can be solved much easier without web workers. Just use rel no opener. We can see that here. So if I run this, it'll be a bit harder to show, but you can see that I opened this one with target blank and this one target blank and rel no opener. So I'll open the bad child window, and this can count, and I click on horrid, and you see the window doesn't even show. Okay, Here it shows again because it finished. I'll do it again. Horrid. Nothing shows. And after 5 seconds, it works. You see, without the horrid, it works perfectly. Let's hope it will work here. No, of course not. Just start it again and open the good child window. Now, the good child window with no opener, I click on horrid, and everything works. I can keep on using my parent window. Okay. Oh. The next thing is promises. What can go wrong with promises? This part, the microtasks. Note that the microtasks run until the microtasks queue is exhausted. So if we have this code that uses microtasks and we do something like that, which is an infinite recursion, if you notice, we'll actually get an infinite loop here because the microtasks queue will never be exhausted. The queue microtask, what it does, it puts this callback inside the microtasks queue. So we have a loop that runs until the length is 0, but this function, this callback, execute adds another one to the queue. It can also happen with promise resolve then. It does exactly the same as queue microtask, and it will cause us something really bad. I have this example. I'm not going to show it because it will get my Mac to overheat, and I don't want to do that. But you can try it at home and be ready to turn off Chrome really quick. The last one, we'll talk about the animation and how it relates to your performance in this part. So, OK, this is bad. It's a bug in slides, I guess. So what happens here is we also always hear about request animation frame versus timeout, set timeout. So let's see an example here. I'm going to click animation by request animation frame, and we see it's moving, and it did 121 calculations of the translate script. Let's see here. OK, so this step, I count how many times I actually do the steps, and it did that. I can do the same with set timeout with 0. It does the exact same animation, only did about 4 times the calculations. So yeah, don't do this at home. And we don't want to waste our CPU, so we'd rather do this. But what if we actually do set timeout with the frequency that we want to do, which is around 16.67 milliseconds? So we get the same results as using request animation frame. Okay, I'll just show you without using the request animation frame. So it's this, and it changes it to this calculation. So 121, 22, depends on when I started. But what happens when I have a rich application that has lots of tasks? So let's enrich the application. I actually do set interval every 100 milliseconds, and I add another set interval. So I'll have lots of intervals running. So I enrich the app, and I'll click on set timeout 16, and nothing happens. Oops, now happens. I'll click on with 0, and nothing happens. Even worse. Boom. But let's use request animation frame, and we see the animation now. What happened? We missed a few frames, but that's expected because our app is heavier. So what happened was that we added a lot of tasks here, and they blocked each other. But when we got here, it was called anyway, okay? Because it was called on almost every event loop cycle. So now we know why request animation frame is better than set timeout. Quick words about Node.js. Its event loop is not infinite. We know it exits if you don't do anything about it. There's no rendering because we don't need to output anything. It has 3 task queues, the events callback, check phase, which you can use with set immediate, and the timer phase, which is set timeout and set intervals. Its microtasks consist of promises and process.nextTick. So the algorithm looks kind of like this. We just, as long as we have tasks, any tasks, we pick one list, and we pop something from this list, execute it, and do its microtasks. Pretty much similar. So we'll summarize. The event loop is a loop, surprisingly. I hope you're now not afraid of the event loop. Beware of long tasks. We saw how they can block your application. You'd usually like to break tasks into smaller tasks up to, I don't know, 50 milliseconds. Beware of recursive microtasks, these little promises. People sometimes don't do them. And we learned why request animation frame is better than set timeout for animations. We also saw it works kind of the same in Node.js, so don't be afraid of doing backend if you don't do frontend. It's exactly the same. So thank you very much. And that's, as Piotr said, it's time for questions. You're on mute, Piotr.
Sorry for that. So thanks so much for the presentation. These talks are always so informative. And can you also promise that you will share your slides so we can try this this event loop that's breaking the Chrome window in the browser?
Yeah, definitely.
Awesome.
I like to spread malware in my slides.
Okay, so maybe you will gain a Bitcoin at least from that. So Tomasz Ciecierski is asking a question. What's the biggest production issue you had in a Node service?
Oh, that's funny. Actually, it's quite embarrassing. I once had a relatively critical service that does something I can't really talk about, but it was like life and death thing. And the server crashed every few hours. And when we looked into it, we saw that someone left Winston logger logging into the disk. And when you do that and you're streaming with Kafka, it might not be such a good idea because, as we saw, read and write also can choke your event loop. It also has memory issues, but there was a really big issue there. So yeah, you should know how it works in order to prevent blocking your event loop.
Awesome. So this is actually a good example because in Python, for example, it would not happen if a similar situation would appear.
Might be, yeah. Actually, you can avoid it in JavaScript if you use a different logger, but
okay.
Yeah, that was the case.
All right. So the next question by Max Basov. The question by Max is, so we should know which queue use in different situations to have better performance, right? If the micro or macro?
Yeah, so I think it's good to know the language that you're writing, like the inner workings anyway, but yeah, you can actually make better code knowing that, because you'll know when to use set timeout and when to use request animation frame. For instance, if you know that you're going to get your data after 2 seconds, don't wait for it with request animation frame, for instance, because you can do request set timeout for every, I don't know, 500 milliseconds, and then save yourself some computation power, for instance. Is that clear?
All right. Yeah, to me it was clear, and yeah, we don't have more questions. So last question from me: do you think we can avoid these issues with animations using CSS animations, or it doesn't matter?
CSS animations. I think think it should work kind of the same, because it will go to the rendering part, it will trigger rendering, but you'll have less JavaScript running. So your tasks will take less CPU, for instance. Right? It depends on the animation, I guess. Some animations go to the GPU directly, some not.